Okay, so for the second part of the class, so we basically finished the wrangling side, right? So you feel free to just close the script. I think it's also a good idea if we, because we're still within the same project, the files are still there. So for us to just get a fresh view on our environment, you can just click on that broom icon, and
Doctor,
that
Doctor
is,
Smith, just have one more question.
yes.
So on my computer that I'm using right here, my environment, I've been meaning to ask you this. It's got the loading symbol, and it's had that all the time I've been working on it. It doesn't say
Oh,
it just has a loading symbol.
okay. But are you still able to run things?
Yes, sir, I'm able to run it. I just didn't know what that meant.
Okay. Yeah, that's I don't think I've seen that before, but I mean, as long as you can
Yes, sir.
run the code, then we should be good. And yeah, so if anyone else, I mean, for everyone that is not having any issues with the environment being loading, just go ahead and click on that broom icon to clean your environment so we start fresh. And also, I sent you an email last night asking for you to download again the GitHub repo and move a code file that I share with you on the GitHub to the code folder on this project. So we're not going to go through that process now, as I'm assuming you already did it. If you did not, you have to catch up on the go. But basically, you would come now on your code folder, and you would launch your yield at is a 0208 yield editor partial. So that's the one we're going to be start working now. So if you want to go ahead and do that, and while you do that, I want to just open the complete version elsewhere. All right, so this script here is going to be, we're going to be doing some of the filters, applying some of the filters that you read on the EO Monitor editor paper, right? So that paper was basically, that software that the paper describes is available. So it is a USDA product that is freely available. And it is definitely one of the main sources for cleaning yield data. It is, however, only, it's a Windows-based software, so you wouldn't be able to run on a Mac if you just have a Mac OS. And also, it's not programming, which has pros and cons. But for me, from at least a research perspective, if I have 50 yield editor or yield monitor data files that I need to clean, doing that by point and click on a point and click software is very time consuming and prone to human error. If I can create a script that automates that cleaning for me, then it's a lot better, right? So I like having the chance of doing things using programming so I can automate those tasks that are, especially the ones that are repetitive, that you have to run for a whole bunch of fields. So that's basically what we're going to be doing here today, right? So our learning objectives are to learn and implement yield monitor data cleaning steps. We're going to be working with some, not all of the ones that you read on the paper. And then we want to compare both numerically and graphically raw and clean yield monitor data and see what happened, what were the points that were cleaned out, what were the ones that remained, and especially how did our statistical summaries change between raw and cleaned? Like how was our mean, how many observations we had, what was the coefficient of variation, all those things that you also read on the paper. All right, so if you come here to the first chunk, we're gonna have to install a couple packages. So if you can go ahead and or remove the hashtag from the first one, so leave sync. What I would tell you is, so especially when we're installing packages like this, just have your cursor anywhere in that line and just push Command Return on a Mac or Control Enter on a PC to run only that line of code. Don't try to run the whole chunk. That's just going to give you too much output to look at. So just run that, install it. You're gonna get that installation output right below it. So do that first for leaf sync, and you can comment it off again, adding the hashtag again, and do that for patchwork next. And just to tell a little bit, so leaf sync is going to be a package that we're going to use to synchronize two map views. We're going to be doing this later in this exercise. And patchwork helps you to combine ggplot maps that were done like separately in separate chunks. You want to bring them together. That's what patchwork does. So that's why we're installing these. Also, please always remember, every time you have an install.packages function, you remove the hashtag to run it, you run it, and then you add again the hashtag. You don't want the install packages function to be active in your chunks, especially when we are rendering, right? That creates issues. So after install, make sure you comment it off again. Okay, so assuming everyone was able to install these two packages and already commented them off, now you can go ahead and play the whole chunk, so you load all the packages that are in that chunk. Also, just to point out again, I did for this time included this chunk option on top. It has to be on top, and when R knows is a chunk option that you're changing because it's hashtag vertical pipe, that's how it knows. And then it has a whole bunch of things you can change about a chunk behavior. I'm just saying message equals to false, because some of these packages here produce messages when we load them. And I mean, it's just messages and warnings. There's no error. So I'm just inhibiting those messages to appear because we don't really use them anyways. All right. So now if you go to the next chunk, the first thing we're going to do is import the data that we just created on the previous chunk, right? So to do that, as you know, that is a GeoJSON file. Well, and let me just clarify something. So the object in R was an SF object. However, there is no SF file type. There's nothing like name.sf. That doesn't exist, right? SF is the name of the object when it's in R. However, when it's exported on your file system, in our case, we export it as a GeoJSON file, which is an actual file type that exists outside of R, right? Just wanted to clarify that. So now we're going to import a GeoJSON file that when it's imported in R is going to be interpreted as an SF object because we're going to be using a readsf function, right? So let's just go ahead, use that assign symbol. You can start typing read_sf. So we open and close quotation marks, and we're just going to get that file. So again, we need to do .. to get outside of the code folder. We need to go inside of the data folder, which is where we exported the file that we created before. And if we hit tab, you should see the yield17 _ process.geojson that we just exported this file on the previous script. So if you run it, you should import, it should, at this point, and now it's something good to notice, if we check this geospatial information, it is already projected CRS at UTM zone 16 because we did that wrangling on the previous step, if you recall. So we shouldn't have to do any of that transformation of CRS at this point. It is already a data frame, already with the clean names, already have the metric system variables as well. So all looking good. We really don't have to do any wrangling with this at this point. All right, everyone was able to, or was someone not able to import the data set? You need to have this because we're going to use this data set below. All right, I don't hear anything. I'm going to keep going. So we imported the data we needed. Now let's just take a quick look at the summary. I left you the code already there. No, this is just the summary function we've been using. So we see speed is in miles per hour, ranging from 1 to 5. Yields in pound per acre is still ranging from 0 to above 4,000 pounds per acre. Again, when we were doing that filtering before was just for plotting reasons, was on-the-go filtering. We were not saving that filtering to an object. So our yield raw data still has that high yielding value that we probably know it's an error. Then we also have yield in kilograms per hectare, speed in kilometers per hour, and the geometry column. Everything, I mean, of course we know we have some errors we have to remove, but other than that, we don't have any negative speed values. We don't have any negative yield values. So at least we know that. Okay, the first thing I want to do here is create a ggplot of the raw map. And then I want to save that map that we're going to create to an object that's going to be called EOMapRaw. So I already left you the beginning of the ggplot and the saving of that to an object. So if you just come to the end here, you're going to add a plus, hit return. If you recall, you're gonna map a SF object, so we need to use geom_SF. The data, that object that we're using is the one that was given at the ggplot level already. So we're just gonna say here, open the AES function and just say inside of it, color equals to yield LBAC for pounds per acre. You get outside of the AES function, add a comma, and you can say size equals to 0.1. So we remove the size of the point. And also I want to add a plus after geom_SF, hit return, and change the scale again. So we use a scale color underscore Viridis underscore B for bent. So if you just run that, you notice that if you just run this first part, the map doesn't appear as it used to. And the reason is we're saving the map to an object. So now if we want to see the map, we have to print that object by calling its name. So if you just do that, then your map appears below. Right, and the reason, and just to reiterate this again, in the past, we were not saving our plots to an object because we didn't need to use them again down the road. In this script, we're going to be using this same plot here a few times. And just to avoid us to have to type the same thing 3 times, I'm saving this to an object. And then I'm just going to call that object name when I need to reuse it in another chunk. So that's the reason. Okay, if you come here to the next chunk, it's basically, so I left you most of the code here. So we're again creating an interactive map. We're going to save that to an object called EOMapRaw int. But it's basically the same map that we just did on the previous script. And because of that, I left you most of the code. One difference here is just that I'm giving the core regions. I'm saying what is the color scale I want to use for the regions, or for the color of the points, which is the Viridis. That's the only difference there. And also I left here 3 dot dots or 2 dot dots for us to just edit a little bit of this code. So if you come here to the end of the CX.1, you add a comma, you come to the line after it, remove those 3 dots, because again, this R doesn't understand 3 dots. It was just a placeholder for me. I just again want to change the size of the outline of the points. If you remember, we did that by using the argument LWD equals 0. So the outline size of the point is 0, meaning it doesn't have an outline. And also the last one here, remove the 3 dotted points, is to change the map type. So again, I want to say map types equals to, and then you already typed this before, but it's esri dot world imagery. Oops, imagery. So esri dot world imagery with E, W, and I uppercase. Dennis, I believe you're not going to be able to run this today, but don't worry, we'll connect after class and we'll troubleshoot what's happening on your side, and then you should be able to run this after that. If you just run this, if when you were doing the previous exercise, if creating the interactive map was taking some time on your computer, you don't have to print it at this point. I'm just going to print on my side so you can see. But if you print it on your site, it should work just like before. And again, I'm saving this interactive map to an object because I want to call this again in another chunk that will come afterwards. All right. So this is just us again taking a look at the data that we wrangled on the previous step. So now is really where we're going to start doing some filtering based on what we learned on the paper. So you did learn that there were like 10 or 12 filters on that paper. And I'm going to show you how to apply 5 of them today, or maybe start today, but not finish today. So the first 2 that we're going to do is minimum and maximum yield. So if you come to the next chunk here, I already left you, I think, all of the code, so you can just go ahead and run the chunk. Just for us to look at this, so this is just a density plot, which you can think of a histogram plot. So the higher is the curve, the more data points we have around a given yield value. So we have most of the points around maybe 1,200 pounds of lint per acre, right? And then we do have some outlying points, and we can see how many we have with the geom rug because it adds a vertical bar below the density where we have a data point. And we see we have 1 data point that's above 4,000, a couple that are above 3,000, but the majority is below maybe 2,500 pounds per acre. Now, I want to bring the paper just very quickly here and show you what we're going to be doing. So this is the paper, right? That you read. You can see how the idea here is very similar, where they have here the histogram. So this is on the paper, they're showing as a histogram. We're showing as a density plot, but it's the same idea. If you were to just draw the outside of this histogram, that's what the density really is. So how did they determine which yield data points they wanted to keep and which ones they were treating as errors and removing? So they basically used this distribution of yield data points, here again shown as a histogram, and they defined some boundaries. So first they define a quantile. So the quantile is basically like how many points if you were to say your data point, your entire data set is 100%. What was the point if you order them from lowest to highest? What was the point that fell? Let's say if I wanted the 10th quantile, what was the data point that was the 10 that represented 10% of my data? Right. So coming from the lowest to the 10%, what was that data point? Or maybe if you go to the 99th quantile, what was the 99th quantile is basically what data point represents 99% of the data when you have it ordered from low to high, right? So that's what a quantile basically is. And you can think of like the 50th quantile is basically the median. So if you know the concept of the median, which is where you order your data from lowest to highest, and you look at what is the one right in the middle, that is your median. That's also the concept of the 50th quantile. So here they used, I know this is a little bit of statistical lingo and talk, but don't get discouraged. I just want you to visualize that for the data set that they showed in the paper, that the 10th quantile was right here, the 99th quantile was right here. They used those values to then produce min y and max y. So min y is basically using the minimum quantile and moving that farther out, and the maximum yield was using the highest quantile and moving that out as well. And they basically removed all data points that were lower than min y or greater than max y. That's what they did. They're using a quantile, which is basically using the yield distribution itself to establish some boundaries, extending those boundaries, and then removing everything that's outside those boundaries. And this concept they use both for yield and speed. So we're going to use this concept here again. We're going to walk through how we calculate those quantiles, how we calculate min y, max y, and how we filter the data based on those thresholds. That's what we're going to be doing next. Okay, so imagine that we're going to have a similar like limits that we're going to be creating for our distribution, right? Because our data is different from the paper's data. It's going to be different values, and we're going to be creating those next. So I just want to show you something quickly here. If you come to the next chunk and you call the function summary that we used before, right? So we already used EO17. So the name of the object, right? So summary EO17W. We already did this above. I just want to show a quick trick here that if I wanted to look more closely into the summary of one variable, of one column of the data set only, you can come here at a $, and that lets you select a column inside of the data. Let's do EO17W $EO pounds per acre and run that. So now instead of having the summary of all the columns in the data, I just get from this column that I selected. And you can just see here, now, if we talk about the first quantile, this is statistical summary given by R, right? So it's not something we're calculating at, but the first quantile that R gives is basically the same as the 25th quantile on the data. The median is the 50th quantile. The mean is just the mean of all data. And the third quantile is the 75th quantile. So R is giving us summary stats based on quantiles all this time, but we never really talked much about quantiles. And I'm just saying this now because we're going to be using them. So again, in R is giving you the 25th, the 50th, and the 75th quantile in its statistical summaries. And we're going to be calculating some different quantiles, but I just wanted to connect that idea of quantile with what R already gives us anyways. Okay, so the first thing that I want to do here is calculate the low quantile. And if I bring the paper again, let me see if I still have that. No. What was the name? It was Sudoth, I guess. Yeah. So just showing you again in the paper, what we're going to be calculating in this immediate next step, which I'm calling low quantile, is this, is the quantile on the low end of the data. So to do that, you just come here at the assign symbol, and R has this function called quantile that is very handy. That you first give it the data that you want to calculate a given quantile over. In our case, that is the EO17. You can just copy from above. It's the EO17 yield in pounds per acre. So it's just that column, right? We're not giving all columns in the data. And then the next argument is the quantile that we want to calculate. So in the paper, they recommended using the 10th quantile. So because in R, the quantile goes from 0 to 1. That's how, it's not a percent, it's a fraction. So to do the 10th quantile, we say 0.1. If you run that and you just run the line below, which prints the result below the chunk, you're going to see that the 10th quantile sits at 551 pounds of lint per acre. So if I go back to the plot just so we can kind of eyeball it, it would be somewhere around here is our low quantile, which is the 10th quantile for yield. Okay. So next thing, I want to calculate the upper quantile, which again, if I bring the paper back, I close again. That's here. So the upper quantile now is going to be this one here on the paper. So for us to do that, you can basically copy and paste this part here that you just wrote above. The only difference is instead of getting the 0.1, we have to edit that part of the code. We're getting the 0.99 or 0.99 quantile to get the 99th quantile. And again, where am I deciding these numbers here from? I'm taking them from the paper. Now, they could have been different values, but I'm just following what the paper suggested. So if we now run this and we run the next one just to print below, the 99th quantile is at 1,939 pounds of lint per acre. And again, if we come to our data, that sits pretty close to here. Okay. Now we're going to calculate the inner quantile range. If you've never, you know what, let me do something quickly here. It's something I'm going to do on the go, so I don't have on the script. I just want to show you something very quickly here. If you have never heard of the concept of the inner quantile range, if you want to code with me, you're welcome to. You don't have to, but I just want to show you on a box plot what that means. Actually, this should be y, and I want to have x equals 1. Okay, so this is just a box plot. So also shows distribution. You can kind of think of a box plot as it's similar to a density plot, but it shows in a different way. So if you've ever seen a box plot, it basically the solid black line in the middle is the median, so that's the 50th quantile. The upper hinge of this box is the 75th quantile. The lower hinge of this box is the 25th quantile. And the difference between the upper and lower hinges of this box is what's called the inner quantile range. It's just basically saying that you have 50% of your data points fall within this box. And then in a box plot, you have the whiskers. So the whiskers extend to some distance away from the 75th and the 25th quantiles. And then you have the points, which are considered outliers, which are extending even beyond the whisker location. But basically, I'm just telling you all this to show you that the inner quantile range visually is basically the box that we're seeing here. And we're going to be now calculating what is this box, but numerically. So if you come down to the chunk here, let me just rephrase something. So the inner quantile range in general is the 25th minus the 25th. That's the concept. For the applications that we're going to be doing here, which again are based on the paper, they're calling the inner quantile range the difference between the upper Q yield, which again is not a 75th in this case, is the 99th, minus the low Q, which again is not a 25th, it's the 10th. For this case here specifically, because we're following the paper, right? So in our case, the inner quantile range is going to be 1,388, which again was just the upper quantile, which was 1,900, minus the lower quantile, which was around 500. But now, why are we calculating this? Basically, because for us to calculate min y and max y, and again, bring in the paper just so you visualize, we have calculated the lower quantile, the upper quantile. But for us to calculate the minimum y and max y, we need to know the inner quantile range to do those calculations. So coming back to our code, the min y is basically, you can use the sign value, is going to be the low Q yield that we calculated above. So you can just bring in the name of the object. So as you know, it's going to bring the value when we run it, minus, and then you open and close parentheses, 25% of the inner quantile range. How do we say that? We basically say 0.25 to mean 25% times IQR, which is the object that we created above. So the low yield, so if we run this, I guess if we look at the numbers, easy then for me trying to explain the math. So the min Y is 200, whereas the low Q was 500, right? So if we look again here on the map, on the density plot, around here would be the low Q, and then about here would be the min Y. That's what we just did here. And again, this concept is connected to the paper. This is how they calculate as well. Now the max Y is going to be based on our upper quintile yield. And now instead of deducting, we want to add. We want to be a plus because we want to extend beyond and not less than, right? Because we're on the upper side now. So it's the upper quintile plus 0.25, so 25% of the inner quintile range. So if you run that, we see that the max Y is now 2,286, whereas the upper quintile was like 1,900 something, right? So we're basically taking the quintiles and extending them outwards. So we define the boundaries of what we want to keep and what we want to filter out. All right, was someone not able to do this? If you were not, let me know, because we're going to be using these in the next chunk.
Professor, I I did manage to run it, but could you please repeat the concept of min y and max y?
Yeah, so first we first find the quantiles of the distribution of the data, right? So the low one is based on the 10th quantile, the high one is based on the 99th quantile, which let me just pull the paper again so we can see. So this is the low quantile, this is the high quantile, right? That's how I'm calling in our code. But the paper then uses them and uses the inner quantile range to then extend the quintiles outwards. So the minimum Y is basically using the quintile and extending that beyond by deducting from this quintile 25% of the difference between the lower and upper quintile. So it's extending the low quintile outwards and that is called min Y. And it uses the min Y threshold to say everything lower than min Y is error. We're gonna filter out. And the same thing with the upper quintile. So it finds the upper quintile and then it extends it to the max Y, and then it then filters out data that is greater than max Y. So in the end, we're really only going to keep data that is within min Y and max Y and filter out everything that's outside of those boundaries. So in our case here, we're just finding those boundaries for our data because again, this is based on quantiles and quantiles are data set specific. There's no value. And this comes back to the question that Dennis had previously. Could we just come here and say anything lower than 1,000 or 100 or whatever, we're going to assume it's error? I mean, we could, but the same field of harvest this year is going to give you a different distribution of yield as if you harvest next year. And especially across different sites, across different years, each site year has their own distribution of yield data. And we want to use that specific knowledge from that site and that year to determine the thresholds that we use instead of using a fixed, somewhat arbitrary threshold.
Like Dr. Bastos is like how they define like 10 quintile and 1 quintile. So they are saying that there are high chances that there will be low speed and low data, and there will be only like very less chances when they have high data.
That's a great question, Marinder. And this is actually something that is one of my critiques of this paper.
So like, sorry, like it will not depend on like raw data which we got from our combine.
Yeah, so that you're exactly right. So let me just rephrase here. So on the paper, they are recommending that we use the quantiles, the 10th quintile as the low yielding side, and the 99th quintile as the on the high side of things. Why? I mean, could we use the 5th quintile, so like 5% instead of 10, to be the lowest? Could we use the 95th on the upper side instead of the 99th? We could. There's nothing keeping us from doing that. And I guess Amrinder is asking, why is the paper recommending 0.1 and 0.99? Why those values specifically? They really don't explain. If you read the paper, they don't explain why they come up with that. I'm assuming it's based on their personal experience. but it's really, they're not really explaining. So this is actually something that these values could change. They could be different depending, and in fact, when we get to the speed filter, these values are different for speed than they are for yield. But in the paper, they never explain why they're different and how they decided those values. So it's one of my critiques of the paper as well. And I'm planning on doing some work on this where we're going to be testing different values and seeing which one represents better reality. Thanks, Arminder. I appreciate that discussion. Anyone has any more questions before we continue? All right, I don't hear anything, so let's keep going. So now my goal, tables and numerical summaries are great, but I am a plots person. I like to see a graph. And what we're going to do next is going to take a little bit of time and thinking, but I think is going to be really, really useful for us to visualize what these numbers actually mean. So my goal, and maybe I shouldn't have closed the paper. I keep closing it. Let me just pull up the paper again. So my goal in the next chunk is for us to basically recreate this plot with where is our low and high quantiles, where is min y, where is max y, but for our data and in ggplot. So that's my goal on the next chunk that we're going to be working on. So if you come to the next chunk, I left you some code there already. If you just run it, it's again the same distribution that we already had above. Just the only difference is I don't have the geom rug here, so we don't have those small vertical bars on the x-axis. So the first thing I want to do is add here a line for us to visualize where for our data low quantile value is. So you come here on the geom, after the geom density, you add a plus because it's ggplot, it's not data wrangling, it's not no pipe, is a plus. Remember that. Hit return, and let's use a geom called geom v line. This stands for vertical line. So the argument that it has is x-intercept. So basically, we're going to draw a vertical line on our plot, and we need to tell it where in the x-axis I want this line to begin. So I want this line to be sitting at where the low Q yield value is. So we just come here and say x-intercept equals low Q yield. If we just run this, it puts a line right there, but I do want to do some aesthetics changes here before. Not using the aesthetics function. Sorry, I didn't mean for that to be confusing. I just want to change something on the go. So I add a comma, I hit return just to break the code. I want to say color equals open and close parentheses red. So I want to change the color of this line to red. Add a comma, hit return. I want to change the type of line. So now is a solid line. I want to change it to something else. So the argument for that is called line type. I want to say line type equals 2. I think this is a dash line. So if we run it, yeah, this is what we get. All right, so we know visually now in our data, where is our low Q? Now I want to do the same thing for the upper Q. So if you want to go ahead and just copy this, add a plus after pasted, we're just going to adapt the code now instead of rewriting everything. So instead of low Q, we want the high Q, right? Because now I want to add the one on the high end. Or sorry, I didn't call high Q. I just noticed now. I called up Q. So UPQ yield. I want to change the color of that to blue instead of red. And I want to change line type to 1. So we had to change all of the arguments here just to make sure you got it. If you run it and it runs properly, this is what it should be looking. So we changed the up Q, color blue, line type 1. So these are our low quantile, upper quantile. Now the next thing I want to do is plot the mean y and max y. Remember that mean y and max y extend outwards based on the quantiles. We can add a plus here. You can paste again what you had copied from before. Now the difference is that instead of low Q yield, we want to have min Y. We leave the color as red, and we change the line type to 1. So this is our min Y in our data. Oh, and I also noticed something here. On the blue one here, so when we plotted up Q, I actually also wanted line type equals 2. I told you 1, sorry, I wanted 2. I want the quantiles to be dashed and the min Y and max Y to be solid. So this is how it should look like. Okay, so you can add a plus again. Now our goal next is going to be to add the max Y. You can just paste the code. We're going to have to do some adaptations again. So instead of low Q, it's going to be the max Y. Instead of red, I want it to be blue. And I want line type to be equals to 1. So as you're running everything, it should start looking like this. So we have the density, we have the dashed lines as our lower and upper quantile, and we have the solid lines as our min and max Y. And then there's one last thing I want to show you here how to do, which is I want to visualize only the data we're keeping. And what that means is all the data between the solid red line, which is the min Y, and the solid blue line, which is the max Y. So to do that, we're going to add one last thing on this plot. So if you add a plus there is a function, a plotting function in ggplot that is called annotate, like that. So this function is really flexible. You can add any different type of geom using it. What I want to do here is add a geom that is going to be a rectangle. So to do that, it has an argument called geom. We say geom equals open and close parent or quotation marks, and we say rect for rectangle. Now, if we just do this, I don't think it even works because we need to specify some other arguments inside of it. So add a comma, hit return. So it's going to be a rectangle that we want to add, right? So the thing is, let me just print again the plot. I want to add a rectangle that on the x-axis, it starts on min Y and ends on max Y. And on the y-axis, it starts at 0 and it can go up to infinity. So we're just going to be saying those arguments next. So it has an argument for y min, for being the minimum value on the y-axis. Again, this is going to start on 0 on the y-axis. We add a comma. It has another argument called y max, which is again where the rectangle stops on the x-axis. For our case, it can be infinity. In R, we can specify that by saying inf, where the I has to be uppercase. We add a comma. So we specified on the y-axis where it starts, where it ends. Now we want to specify on the x-axis those limits. So the minimum on the x-axis, so the x min, is going to be our min Y. So min Y is our min yield, right? So don't get confused between min Y and Y min here. Y min is an argument of the annotate function. Min Y is the object that we created representing our min Y, which is the solid red line. You can add a comma. We now specify the x max. So the maximum value where the rectangle is going to stop. That's going to be our our max Y. So if we run this, oh, nice. I mean, we can't see what's behind it. So it's not very useful at this point. So I want to change 2 more arguments here. So one is if you add a comma here return, I want to change transparency. For that, we say alpha equals, I want to change to 60% transparency, that is 0.6. So if we do that now, we can see through the plot or the rectangle. And I also want to add another argument here, I just want to change the color of the fill of this rectangle. So we say fill equals, I want to open and close quotation marks and say green. Okay, I want to show you the code in case you're still catching up. But this is what we see now. Oh, sorry. I'm just going to scroll lower so you can see. So this is basically the plot where we plot our low quantile, upper quantile, our min y and max y, and then the green rectangle represents the data that we're keeping, right? So everything outside of the green area, we are discarding as at least for based on yield, right? So this is the yield variable that we're looking at.
You're missing a column. No.
Sorry, did someone have a question?
I have an error here in Tifton. It's caused by error in quotation compute underscore geom one. Geom ret requires the following, missing aesthetics, and then colon x max.
Did you make sure that you have a plus here that's connecting the last geom line with annotate?
Yes, sir, I do.
Okay. Well, we can, yeah, I'm not sure why that's the case. I would have to look at your code as well, but we can troubleshoot this later. And I mean, now for a class, it's not a big deal if you're not able to do the annotate with the rectangle, but I just think it's a nice thing to know how to do as well. So we can troubleshoot that after class.
Yes, sir.
Awesome.
Can I see your code real quick one more time?
Oh yeah. Yeah, I would say like make sure that you have your pluses at the end of the geom lines at every step. Make sure you're closing your parentheses, or sorry, your parentheses at the right place, right? And a good way to know where a parentheses is closing is if you just have your cursor and you go like before and after it, it blinks what is the parentheses that is closing, that is related to. And another thing that could have happened is make sure you have your
It was a spelling error.
Okay, awesome.
I put X max instead of X max. So I'm
Nice.
sorry.
Nice. Yeah, these code troubleshooting skills are definitely something that we develop over time and is a really useful skill, because when you start working with your data, you're going to have issues. So being able to troubleshoot small things like missing a comma here or maybe a parentheses, all the way to troubleshooting more complicated things using Google and Stack Overflow are really, really useful skills. Okay, so let me tell you this. All the way up until this point, we have defined our boundaries based on the data. We have visualized those boundaries. We have not filtered the data yet based on what we just did above. So to actually implement the filter, go to the next chunk. I left you the name of the object that I want to save the results already. So that's going to be yield 17 WYF for yield filter. The Y just represents that we're applying the filter based on yield data at this point. So you can just use your assignment symbol there. We're going to start with our incoming data set, which is the yield 17W, right? So that's the one that we use to create everything above. Let's use a pipe to connect it, and then we're going to use the function filter. However, now it's going to be a little bit different than what we've done before. So I'm just going to print yield 17W below here so we can see. We're going to use the column yield LBAC for pounds per acre. That's the column that we've been calculating all of the thresholds above, or based on that column. So I want to keep the yield pounds per acre values that are, well, I guess before I tell you the code, let me open for some thinking here. So I already told you, right, that we want to keep the values that are greater than the min y and lower than max Y. So basically what we're seeing on the green rectangle here. How can someone help me to at least start thinking of the logic that right now it's human logic in words? How can we represent that human logic in code? Anyone has can help me to start thinking of this?
Can we add like greater than and smaller than sign with the mean Y and mean max Y?
Yes, Shikar, you nailed it. Okay, so what would you type here? What would you tell me to type here? Oh, I think you're muted.
The greater than sign.
Okay.
And mean Y.
Yes.
And I think the syntax for the and is like an ampersand. And again, yield, yeah, and lower than sign, and then max Y.
You got it. That's exactly it. Thanks, Shakar. I appreciate your help. Yeah, so we're basically, putting into words here that we want to keep yield values that are greater than min Y, right? So that threshold. And also, I mean, if we stopped here, we would have been just applying the filter based on the minimum boundary. But then we also have this end, meaning that we're only keeping points that fulfill both conditions. So for a point to be filtered in or to remain in the data set, it has to fulfill both of the conditions of being greater than minimum Y and lower than max Y. That's exactly it. Thanks, Jakar. So if you run this, if you're able to type that and you run it and we print it, right? So before we applied the filter, we had like 31,724 observations. How many do we have now? Let's see, can someone in Athens just help me to inspect this and spell out?
30,385.
Yes, so 30,385, that's right. Thanks, Amrinder. So we basically removed here, over 1,000 data points using the EO filter, right? So this is just so we're seeing, or at least understanding how much we're reducing at each given point. Okay, so if we come to the next chunk, I just want to do a quick summary on the filtered data, right? So for that, we're going to use the function called summary. The name of the object now is what we created above. So it's not yield17w anymore. It's yield17wyf, right? That's what we created above. And I want to get a summary of the yield pounds per acre column. So if we do that, we see now that the minimum value is 204, the maximum is 2,282, and here's the median and the mean. And if you stay here, so stay where you are right now, I want to go up on the code and see the raw summary for us to just inspect that. So here it is. So looking at your screen and looking at mine. So on mine, I'm looking at the summary of the raw data before filtering for yield. The minimum was 0 and the maximum was 4,274 with a median of about 1,200 and the mean of about 1,100. Right, so we see that minimum and maximum definitely changed. It had a little bit of an effect on median and mean, not huge yet. Okay, so we basically finished applying the first two filters, which were minimum and maximum yield. So next step is going to be for us to apply the speed filter, right? So if you just come on the next chunk, you can just print, I think I left all the code, excuse me, all the code already for you. So you can just go ahead and print it. We have seen this plot in the past, so there's nothing new. Is the raw speed data. We already talked about that. Speed is probably not, like the speed data itself is not error. There's no errors in that, but it's more the effect of low or very low or very high speed values that they can have on yield that's been estimated, right? So that's what we're going to try to do here. If you come to the next chunk, let's just check a summary of speed right now. So we have speed, ranging from 1 to 5 with mean and median close to 4.7. So if you come to the next chunk, we're basically going to be calculating the same quantities. So the low quantile, upper quantile, and then min, I think I'm calling min V for velocity, speed, min V and max V. And I try to use velocity here because that's how they refer to in the paper as well. So we maintain that parallel syntax between what we are doing and the paper. Okay, so as you know, to get the low quantile, we're going to use the function quantile. And now make sure that you specify the proper data set here, which is going to be the, we're going to use the raw data. So not the EL filter data, but the raw data. So the EL17W, and we're going to ask for this quantile over the column speed miles per hour. And then the quantile that we want to ask is the 8th quantile. So the way we say that is 0.08. If you run this and you print low speed, the 8th quantile is at 4.6. So we can really see how like the majority of the points were between 4.6 and something else, even though we had some that were at 1. Anyone had a question? Excuse me. All right, so we defined the low quantile for speed. Let's now define the upper quantile. So again, we use the quantile function. I mean, you can basically copy and paste the above pretty much. And we're just going to change now instead of the 8th quantile, we want the 99th quantile. So to say that, we say 0.99. And this is that upper quantile. If you run it and you print it, the upper quantile is 4.6, or I'm sorry, 4.8. I guess I said 4.6 because I just wanted to tell you that the low quantile was 4.6, the upper was 4.8. So we really see this data is really concentrated around those two values. Now I already left you the formula for the inner quantile range, which is just the difference between the upper and the lower, and that is 0.2, so a very small range. And then I already left you the formulas as well for the mean V and max V. And just something to notice here, and again comes back to the comment of both Dennis and Amrinder, is the paper suggests using 18% of the inner quantile range for speed. However, if you recall for yield, which we just did above, it was 25%. So this value was 0.25. Again, where do they come up with these values? They never explain the paper. So it's again a critique I have for the paper, but we're just going to follow what they're proposing. Right, so our minimum V is going to be 4.56, our max V is going to be 4.8.
And the lower quantile 0.08, not 0.01.
Yes, that's true. Thanks, Dennis, for pointing that out. That's also true. So here, another difference, as Dennis pointed out, is on the yield we use 0.1, so 10th quantile on the low side, whereas for speed we're using 0.08, so the 8th quantile. And again, that difference, they never defended why that choice in the paper. So I don't have a good answer, but the goal here is for us to follow what they're proposing in the paper. But of course, it's always good to be critical when we're reading papers, because just because it's published doesn't mean it's a fixed manual. There's always room for improvement, regardless of what publication it is.
Dr. Baston,
Yes.
It won't mess us up with the IQR for the speed and IQR for the yield being having the same assigned name, will it?
That's a great point. I have not even thought about it when I was making this, but yes, it will. So if you and here's a great case for why I don't like to save objects in between our sessions. So we're working on this today. We're going to be working on this Friday. On Friday, I want to ask you to basically clean your variables before we start. And the reason for that is, that's a great point. Thanks. Was that who mentioned that?
Miller.
Miller. Thanks, Miller. So this applies here, but really applies to any object that we create in R. So Miller was noticing that even though the low Q, up Q, min V, and max V were named differently in the script between the yield filter and the speed filter, the IQR was named the same. And he was asking if that would mess up if we have to redo the yield again. It could, right? So, and this was actually, you know, I could have named the IQR speed here. I guess I didn't even think of it. But that's a great point because yes, if I do calculate here this IQR, which for speed is very small, right? It's like 0.2. And let's say for some reason, I want to go back to the yield part now. So let me get to the, let's see. So I just went back to the yield one, which again, different values, right? Different column that we're looking at. We're looking at yield. If you recall, the IQR for yield was a lot larger than 0.2. So if I just come here and I just recalculate min y, max y, without rerunning the IQR, I would get a min y and max y that are based on the IQR of speed, which is definitely not what we want, right? And so you can see how sometimes you're doing something on a script and maybe you think, oh, maybe let me just quickly rerun something above and continue. If you have objects that may have the same name or maybe something like that, you can really get your analysis confused. Of course, in this case, if we come here after we develop the entire script and we render it, or maybe we rerun the whole thing, that is not going to be an issue because it's going to run in sequence, right? It's going to run the yield first, calculate everything, including IQR. It's going to keep going, and when it gets to speed, it's basically going to calculate another IQR, and it's going to override the previous IQR of yield. But because after recalculating the speed of IQR, we're not really messing with yield anyways. So as long as you don't do any of these calculations based on yield afterwards, it shouldn't impact, and it doesn't impact in this case. But that's a great point. Thanks for bringing that up and opening that discussion. All right, so I basically left you the entire code already now for looking at the distribution and the boundary. So please go ahead and run it. It's really the same code as before. It's just, I was just changing the name of the objects to reflect the ones based on speed, right? But really here we can see again that, you know, both, so if we look at the dashed line, which is the quantile, so the 8th and the 9th, I mean, they're set in a given place, and then they're really going outwards a little bit when doing the min V and max V because the inner quantile is so short, right? Because that extension depends on the inner quantile. And the inner quantile, again, is a reflection of how spread this data is. Because speed is very concentrated around 4.6, the inner quantile is small, and by result, how much you extend the min and max V is also small. So again, in this case, we're just keeping only the data that is within the green rectangle here, which is again from min V to max V. And again, if you come next, we're going to express that in code right here in the next chunk. So I'm naming this object here yield 17 WSF. And now looking in retrospect, I think calling this SF may be a little bit confusing. But I'm calling SF because it's the speed filter. That's why I intuitively wanted to name. So if you just use the assign symbol, Now, because the filters are applied consecutively, what I want to do is not filter based on the yield 17W, but apply based on the yield yield 17 underscore W underscore YF, which was the data that already has fewer rows because we have already applied the yield filter to it. So we're going to apply the speed filter to the one that have already received the yield filter. So that's where we start. We add a pipe, hit return. Again, we're going to call a function called filter. And now let me ask someone else now that that hasn't spoken much. Let's see here. So I want to maybe call someone in Athens, but someone not Dennis and not Amrinder, because you've been helping a lot already. So someone else, help me to think about the logic here to apply the filter that we need. Anyone wants to jump in?
Would it be speed MPH greater than min V?
Yes, and sorry, who was that?
David.
Awesome, thanks, David. Yes, that's exactly right. But so that is basically telling us everything greater than min V, right?
And then
What-
and speed MPH less than max V.
That's exactly it. Thanks, David. Appreciate it. Yes, that's exactly it. So if you run this now and you print it, notice now we have even less number of rows, right? So we have 28,950. So we removed about 1,000 rows on each one of the filters. On the yield was about 1,000, on the speed was about 1,000. But this can be more or less. It really depends on the data. Okay, well, let's see. I think we can just check the summary to finish today's class, and then we can stop here. So the summary, we're just going to call the function summary. We're going to ask for this object that we just applied the filter. So yield 17W SF, use $, and ask for the speed. So now the speed is ranging as we would expect from 4.6 to 4.8 because those were the values of min V and max V. And then let's also just explore, let's add another summary here and explore the yield. How is yield now changing? So yield in pounds per acre. So yield remains, the minimum remains the same. So probably the low speed values, remain the same as from the base only on the yield filter. I think there's probably a little bit of a change on the median and mean, and I think the maximum is also pretty similar. So maybe the speed still didn't have a huge impact on yield, even though it removed 1,000 points. Okay, so we can stop here. So basically today we applied 4 filters already. So mean and max speed, mean and max velocity, mean and max yield, mean and max speed or velocity. And the last one we're going to be applying on Friday is going to be the position filter, which is going to be using the field boundary. So make sure that you got the field boundary that I shared last night on GitHub and move that into your data folder so we can start on Friday from here. All right, that's all I had. Your attendance was through the quiz, so I will, hopefully the discussion that we had was helpful as far as, understanding what I was looking for in the quiz question. If you have any other questions or comments, please let me know. If you have any issues on code, please send me an email right after class now, and I'll send you a Zoom link for us to connect and troubleshoot. All right, thanks everyone.